Yeah. So the basketball, these they don't work in court. Are they playing basketball during the? No, but our Tues could scratch in the court, and then what, it's like, my car. It's a weekday. We haven't finished it for what? Oh, then what do we do? They said they can have.
Let me go over some additional notes, and then we can talk about what's going to be on the test and what we're doing to kind of work towards that. Okay, so first semester, we learned how to find from position to velocity to acceleration. And S sub t, a lot of times that's the notation that we use for position. And then we know to get to velocity, we find the first derivative. To get to acceleration, we get to the second derivative. Okay, and or you can think of it as P of t for position. But we understand this process, right? From position to velocity to acceleration is just the next derivative down. First derivative is velocity, second derivative is acceleration. Now, we want to be able to know how to work back up that chain using antiderivative. So the process of getting from velocity up to position is displacement. So displacement is how far you are from where you started. So displacement is just the depth integral from A to B of V of t. Okay. So if I take the antiderivative of velocity, that will produce position. So if I were to work this out, the integral from A to B of V of t, we know velocity is going to rise up to the position level. So we can either think that as P of t, S of t, or X of t. So let me just use X of t, for instance. So once we have the position function, or once we have the antiderivative, then we work in the upper and lower bounds. So that's just going to be X of B minus X of A. So X of B minus X of A, that's just the difference in distance from the first point to the second point. Okay. And we call that displacement. Okay. So displacement is simply the integral of velocity. Now, distance is the total amount that the particle has traveled. So distance is the depth integral of A to B of absolute value of V of t. What that really means is any negative direction distance that I traveled, I count that as a positive value. So for instance, let me show you what I mean by this example below. Suppose the graph below represents an object. Suppose the graph below represents an object's velocity function. The number inside each region represents the area. The number inside represents the area of that region. So the 10, the 2, and the 3, this really tells us how much the object has traveled. So if I were to accumulate all the velocities of the object, the area underneath would tell me how far this object has traveled. So if this object is moving along a horizontal line, this 10 would mean that it's moving 10 to the right. What do you think this 2 is going to do? 2 to the left. And then this means 3 to the right. Okay. So the displacement just means how far you are from where you started. So I move 10 to the right, 2 to the left, 3 to the right. How far am I going to be from where I started? So my displacements, I'll use the integral notation. Is 10 minus 2 plus 3, which is 11. So displacement is where you keep track of all the positives and negatives, right? You walk forward 10 steps, you walk backwards 2 steps, you walk forward 3 steps. How far are you from where you started? You're 11 steps away from where you started. The distance, however, represents how many steps you actually took, okay, which is different than what this number says, right? This is this is how much progress you've made from where you are. And the distance is really, think of it as in terms of, okay, how many steps did I actually take? It's gonna be a different number, right? Especially if there's a change in direction. So what's the total distance gonna be? 15. Okay. So do we understand that distinction? Okay. Displacement is how far you are from where you began, and total distance is, think of it for steps, how many steps you actually take. So if we understand that velocity is the derivative of position and acceleration is the derivative of velocity, then it should make sense that velocity is the antiderivative of acceleration and position is the antiderivative of velocity, right? If you're moving back up that PVA chain, then you're just taking the antiderivative. Okay. So again, I'm just gonna we have a lot of different variations of position. It could be S of t, it could be P of t, it could be X of t. Those are the most common ones. Okay, V of t is velocity, A of t is acceleration. So the derivative of position is velocity. The derivative of velocity is acceleration. We know that to be true. We learned that first semester. But the antiderivative will bring me up that chain. So the antiderivative of acceleration will be V of t plus c. Okay. This is because there's no balance involved. There's no balance involved. We have to have a function, so a plus c is going to remain. And if I take the antiderivative of velocity, that will bring me up to position plus c. The relationships that we established from last semester still holds. Speed is increasing when acceleration and velocity have the same signs. Speed is decreasing when acceleration and velocity have opposite signs. Okay, let's go to the back page. Sorry, page page 2. Okay, so this f prime, let's think of this as the velocity graph. Okay. Okay. So again, the area inside these spaces indicates how far this object has traveled, either forwards or backwards. Okay. So again, the area between the velocity and the position and the x-axis indicates how far the distance that they've traveled and in the direction that they're traveling. Okay. So these are just a bunch of triangles. I'm just going to fill these with numbers, and then we're going to talk about visually what this means. Okay, so this is a triangle here, 1/2 base times height, 1/2 1 times 2 is 1. But I'll put a negative here as a reminder that we have an accumulation of negative values. Let's split this up here. So this triangle here, 1/2 base times height, 1/2 1 times 4 is 2. This big triangle here, 1/2 base times height, 1/2 2 times 4 is 8. 8 divided by 2 is 4. So this full thing is 4. Okay. This is again 1/2 base times height. This is just 1. So if this big triangle is 4 and that portion is 1, then this must be what? Must be 3. Okay. We could also go through trapezoid rule and trapezoid area formula and get the fact that it's 3. But we can also just use it as a triangle within a triangle and subtract 4 minus 1 is 3. Okay. Okay. So I want to talk about what this means here. This means that this object is, again, let's assume that we're moving just left and right. Okay, so what is this object going to do here? Moving to the left 1 unit, and then at 1, he's going to, velocity 0 means he's stopping. And then from 1 to 2 seconds, he's going to turn around and move 1 unit to the right. He's going to speed up. And then between 2 and 3, he's going to travel how many units? 3 units. And he's going to slow down slightly, but he's still moving to the right. But he's moving 2 units to the right. Okay, does that make sense? So he's just basically he's moving to the left 1 unit, he's stopping, and then the rest of the way he's moving to the right. All right. Does that make sense? Okay, so I want to have that. Once you have that that visual picture in your head as to what this what's happening with this object. Okay, so a little bit of first, we're going to connect some first semester and second semester material together here. It says find the x-coordinate of all relative extrema. So relative max, relative min, we know from first semester, if we're looking at the derivative graph, anything on the x-axis means slope 0. Anything above the x-axis means moving to the right. Anything below the x-axis means moving to the left. Okay. So if I want to create a slope sine line, starting at 0 and I'm ending at 4, where's my slope going to be 0? Where's my critical point? 1. And then to the left of 1, I'm moving negative slope. Below the x-axis and to the right, positive slope. So find the x-coordinate of all relative extrema. X equals 1 is a relative min. Okay. Find the x-coordinate of all points of inflection. So first semester, we learned that if a derivative graph is rising, that means it's concave what? Up. If it's decreasing, it's concave down. Any peaks and valleys is the what? Point of inflection. Okay. So positive slope means concave up. Negative slope means concave down. Okay, so I want to talk about this rearranging of first theorem. Okay, so I have this on this formula sheet here. I want you to look at this first theorem variation. Okay, we know that the integral of velocity will bring me up to position, right? And then I do x of b minus x of a. So this is my first theorem here. Now, if I rearrange this, if I do x of v on one side and I add x of a to the other side, this is really good for particle motion problems because a lot of times we're looking for final position. So if we think of it in terms of this format, just rearranging it, I think this is really helpful. And we're also going to use this a lot, not on this test this week, but we're going to see this next week on that calculator portion. So I want you to understand that if I'm looking for a physical final position, I want to know where I'm going to start off at, and then how far I've traveled from that initial point. Okay, so final position equals my starting point plus however much movement I'm going to make after that. Okay. So if I think of it in that perspective, final position equals initial position plus displacement. So displacement, we can just rely on the numbers that we see below, but I want to just have us practice with these notations here. If I want to find f of 1, starting position is always going to be whatever is given to you. It may not always start at 0, but it's always going to start at whatever point they give you. That's your kind of your anchor point. So if I'm starting at location 1, and from in that interval, I move backwards 1 unit, where am I going to end up on the number line? Zero, right? So this doesn't tell me where I end up. This just tells me which direction that this object is traveling in that moment in time. So between 0 and 1, he's moving backwards. We're told that he's starting at location 1 and he's moving backwards. So he ends up at 0. Okay. F of 2. Again, we can start at f of 0. That's what's given. And then we can accumulate how far he's traveled in which direction in those 2 seconds. So again, he starts at 1. And then between 0 and 2 seconds, how much is he going to travel? 0, right? Because he's going to go backwards and forwards. So he's going to end up back at location 1. Okay, we can bleed into part D here. We're just using the same data. So let's say F3 is my starting location plus however much I traveled between 0 and 4. So again, I'm starting at position 1 at x value 1. And then between 0 and 3 seconds, how much net gain am I going to make? 3 units to the right, so plus 3. So I'll end up at location 4. Okay, f of 4. Again, I'm starting at position 1 because that's what they tell us. And then from 0 to 4, how much net gain am I going to make? 5 to the right. Yes. Sorry, f of 3. Oh, sorry, you're right. 0 to 3. My bad. Thank you. 0 to 3. Okay, state the absolute extrema. Absolute extrema is just the furthest right and left that we experience in these values because we have all the critical points accounted for. Absolute max is 6. Absolute min is 0. Okay, part E, find the total distance traveled from 0 to 4. Imagine you're just taking steps, regardless of whether you're moving forwards and backwards. What's the total distance? Yeah, everything is counted as positive. So 1, 2, plus 5 is 7. The total displacement, however, is the net gain. So here we keep track of the negative and positive. What's the total displacement? Just 5, right? Negative 1 plus 1, that goes to 0. 0 plus 5 is 5. Okay, you'll see this on the next week's test, but I want to show you the notation. Total distance would be from 0 to 4, absolute value of v of t dt. And then total displacement has no absolute value. Okay, so next week I'll ask you to use the notation to justify your solution. Okay. So absolute value means you're converting all those areas to be positive. Total displacement is you're keeping track of all the negatives and positives, and then you're adding them up. Okay, from 1 to 3, is the speed increasing or decreasing? From 1 to 3, we just compare the signs between first and second derivative. We see from 1 to 3, they're both positive, right? Concave up and positive. That's going to mean that's going to mean speed is increasing. And then from 0 to 1, what about from 0 to 1? Speed is what? Negative and positive, so therefore speed is opposite signs mean speed is what? Decreasing, yep. I'll come back to part I a little bit later. I want to just focus on the parts that we are going to be relevant to us leading up to this week and next week. Okay, you guys can turn to the formula sheet here. I want to talk about what we need to memorize and what we don't have to worry about. Okay, so this is not a formula sheet that you get to use on the test. This is a formula sheet that you can use to study for the test. First thing is no summation formulas will be on the test, so this is out. You do need to know trapezoid area. Okay. That continues to be important. You need to know power rule for derivatives. You need to know trig derivatives. But if you know your trig derivatives, you really also know your what? Your trig integrals, right? So I don't want you to feel like you have to memorize this and this one below. So this is just for your reference, but understand that if this is at the top of your page, you can get to all your trig integrals, right? Yes. Yeah, so right now I'm highlighting what you need to know for part 1. Yeah. Part 2, there's not a whole lot of you really start to be able to work through calculator problems. So there's not a lot of heavy calculations that you got to do. Okay, so all the calculations that you do by hand is on the non-calculator. Okay, make sure you also know power rule for antiderivatives, right? This is what what we've been learning recently. First theorem, not so much memorizing. Well, really just applying it, like, how to work the bounds, right? You find the antiderivative, and then you do and then you plug in the half bracket, plug in the bounds. So really just kind of more application. We talked about how second theorem is a way of shortcuts, because your derivative and integral cancels out. You just keep your function, plug the upper bound, multiply the upper bound's derivative. These variations are really good for the second test and beyond. So you really don't have to worry about this for the Friday test. Okay. And I'm just going to highlight trig integrals because we know that these are the integral rules, but again, really you're just memorizing these to get to the one below. And then also average value theorem. And average value theorem is just a rearranging of the height formula for rectangle. So think of it as, if you understand that height of a rectangle is just the area divided by the width, then really that's what this is. Okay, the width is b minus a. The area is that integral from a to b of f of x. You're just dividing it, but it just looks like this form here. Okay, so if we can turn to page 9. It says quiz review, but I haven't done a quiz for this section in a while, so really I'm just going to be calling it a review. Okay, the key is on the back, so if you're working ahead, you're more than welcome to use the restroom. Yeah, you work ahead of me. Okay, so number 1, it says, given our function is x squared minus 2x plus 3, find the average value. So this is hinting that we want to use average value theorem. Okay, what are our a and b values? 0 and 3, right? So just put everything in, you have your function. So let's just set everything up. Okay. All right. What's the first thing we have to do? We plug in the bounds to begin with. Okay, bounds is the last thing, right? We don't want to, the 3 and 0 has nothing to do with this x squared. So we first have to find the what? Find the antiderivative, right? We got to go through a power rule process. Once we get this integral and dx resolved, then we can work in the 3. Okay. Okay. We apply power rule. We know the 2's canceled out, and then now we're ready for the 0 and 3. Plug in the upper bound first. 3 goes in for all the expressions, minus big parentheses, followed by 0. But the nice thing with 0 is that it just goes away. Okay, this reduces to be just what? 27 over 3, which is 9. But is that the last of it? We still have to worry about what? The 1/3 in front, right? So you have the area component. You still got to involve that width component. So 9 divided by 3, or 1/3 times 9, is our average value. That's part A. Part B says, find the value of C. Another way of thinking C value is the X value. So basically your average value is your Y. So how do we find the X? Now, involve the original function, right? Take your average value that you found, insert that in for the Y slot, and you're solving for X. Conveniently, the 3 goes away, so no need to go through trinomial factoring. We can just take the GCF out and solve for X. Now with mean value theorem, we cannot involve the endpoints, but with average value theorem, endpoints are okay. So my interval is from 0 to 3. 0 does land at the endpoint, but 0 is okay for average value theorem. Okay. So we have two C values. Okay. Derivative, mean value theorem, we can't keep anything that lands at the endpoint, but average value theorem we can. Okay, number 2. Again, average value theorem. All right, first things first. What do we do first? Yeah, antiderivative, right? So secant squared, what's the antiderivative of secant squared? Tangent of x. All right, we gotta recall our unit circle values. You gotta know that for the test as well. So upper bound first, tangent of power 4. If you don't recognize negative pi over 4, you can always add 2 pi to it, and it's really the same thing as 7 pi over 4. So what do you guys remember? What's tangent of pi over 4? Tangent is negative in the fourth quadrant, so 1 minus negative 1, which is equal to 2. But is 2 our average height, average value? We still got to involve the width here, right? So pi over 4 plus pi over 4 is 2 pi over 4, which is pi over 2. But that pi over 2 is in the denominator. We're going to flip that up, make it 2 over pi times 2. So 4 over pi. Sorry, yeah, 4 over pi, not 4 pi. All right, number 3. Three says, find the derivative of this antiderivative or this integral. So we have second theorem that's available to us. We know second theorem says, if I were to pair a derivative and integral together on top of the same function, I just plug the upper bound into the function and multiply it by the upper bound's derivative. So these two operations cancel each other out, but there is a little bit of a leftover affecting this upper bound because that's a variable. So first thing we do, replace every t with the upper bound and then multiply the expression by the upper bound's derivative. So we're just following what this rule says, right? F of p of x, that just means inserting my upper bound into the function. That's what I'm doing here, multiplied by the upper bound's derivative. So negative 2x squared becomes negative 4x. Do some cleanup here, multiply all the numerators together. Negative 2, negative 4 is positive 8. On the key, I reduced, but you don't have to reduce your answer. Okay, number 4, similar process, but do you notice anything that is a little different about number 4? There's 2 variables, so we got to do this process what? How many times? Twice, right? So upper bound, we do the same thing that we did here, minus, and we do the same thing with the lower bound. Upper bound into the function here. I just converted that to x to 1/2 just to get it ready for power rule, but you can leave it as radical until later. But here I want to do power rule here, so that's my f of p of x times p prime. But lower bound is also a variable, so I got to repeat the process. The lower bound, insert the lower bound into the expression. Times the lower bound's derivative. Okay, I just took this term here and I distribute it through the parentheses. Okay, if you turn to page 23, these are what you can expect on the test on Friday. And I also have 2 review worksheets in this packet that looks very similar to the test. So you're going to have to do power rule for integrals, which we've been practicing with, use substitution, and change a variable. We did that yesterday, and we'll practice some more. Trig integrals, we just saw some of that with average value theorem. Depth integrals involving unit circle values. We did some of that today as well. The only thing I haven't gone over yet is the absolute value function for depth integrals. This is going to be an easy process. If you can draw your graph, then you can just add the two areas of triangles. Okay, so I'll go over that specifically, but this should feel like a easy problem once we get through it. So I'll do that tomorrow. We did even and odd functions yesterday. We'll practice some more tomorrow. Second theorem of calculus, we just did that, canceling out the derivative integrals. Average value theorem, we practiced some of that as well. And then from second derivative, from acceleration, move your way up to the position function, take the antiderivative twice. We've seen some of that as well. So we're kind of closing in on what understanding what we're going to expect on the test. I have two test reviews on page 13 and also page 17, and the keys are also attached. I'm also going to continue to have help sessions. I have one this morning. I recorded it, and I'll put that on the website tomorrow. Tomorrow 3:30, Thursday 7:30, and Friday 7:15. I'm going to do a little bit of calculator work tomorrow, but I want to spend a chunk of time reviewing, going through practice problems. So tomorrow and Thursday review, Friday tests. All right, go and get your phones.